Now, Patrick, we've been talking about meteor showers. We've been talking about um, comets. We've been talking about asteroids and all sorts of things tonight. But what's the connection between them? Why do they happen certain times of year? Why are these meteors appear to be coming from a certain direction or a radiant, as we say? What do you have for us? I know you've prepared some things to explain all of this to us.
Yeah, sure. We'll go to this table here. This basically is a list of some of the major meteor showers that you can see throughout the year. And one of the strongest amongst them is, of course, we just talked about, is the Perseid meteor shower. On the right-hand side there, you can see there's a parent body associated with each of these meteor showers. And the Perseid meteor shower, the parent body associated is Comet Swift-Tuttle. It's a comet. It's a huge comet with a nucleus of about 16 miles across, and is much larger than Halley's Comet, which is roughly about 9 by 5 miles across. And this image was taken when it was last close to the sun back in 1992, just over 30 years ago, when it passed by. Now, what happens during a meteor shower? Well, these comets leave trails of dust as they go by the sun and in its orbit. And each year, we pass through, for the Perseids at least, the Earth passes through the densest part of the trail, and we get a maximum that occurs usually on the night of the August 11th through to the morning of the 12th. And we're basically, the Earth is plowing through this trail of dust left by Comet Swift-Tuttle. Now, the dust particles themselves can be as big as grains of sand and much smaller than that. And they literally hit the Earth's atmosphere at speed of 100,000 miles per hour, which is incredible speed, so fast that friction with the air causes them to glow. So you get this plasma that forms, the glowing plasma around these particles. And that light from that plasma is the light that you see as a meteor, which only lasts for a brief moment, a few seconds or less. And the other part of it is they come from a certain part of the sky. And this is caused by the Earth's direction of travel in its orbit around the sun, which makes the meteors appear to radiate from the constellation of Perseus, hence the name the Perseids, because that's the name that the shower is named after, from where the constellation they radiate from. So they can radiate from all directions and all across the sky. So if you're watching the Perseids, you don't normally have to look directly at the radiant. Basically, the meteors are all over the sky. You can look anywhere in the sky to catch a Perseid. Now, this year's shower was actually documented with this graph here. The vertical scale represents ideal conditions of how many meteors a single observer can see per hour. And during the peak, usually it's the 11th through to the 12th. In this table here, actually this graph, you can see roughly there was a peak kind of roughly around the 13th and the 14th, which is in the universal time, which is kind of corresponds to our time here on the Pacific coast. And the rates were roughly kind of normal, roughly about 60 to 70 meteors per hour under clear dark skies. Now, something amazing happened this year. If people were staying kind of in a national park and stayed a little bit longer, they actually could witness about 1 a.m. on the 14th of August, an unusual outburst from the Perseids, which brought the numbers up to close to 150 meteors per hour, which is amazing. So that was a bonus for this year, which of course we don't know, because usually the trail of dust is not always evenly distributed. So the Earth just happened to run into a dense clump of dust at that time. Now, the other major meteor shower in the year occurs at the end of this year, which is the Geminid meteor shower on the night of the 13th and the 14th, which is its peak. And the parent body associated with this meteor shower is actually an asteroid. Its name is 3200 Phaeton, and it's a small object, actually an asteroid, roughly about 3.6 miles across. And this is a radar image taken by the Arecibo Observatory. It's really hard object to see because it's so small. And it has an orbit that takes it very close to the sun, closer than Mercury's orbit, where it outgasses. And the recent studies have shown that it gets really hot when it's close to the sun and outgasses sodium, and that may and also some of the rock may vaporize and vent into space, causing it to brighten like a comet when it's close to the sun, and even dislodge pieces of rocky debris as it moves around the sun. The interesting thing is that all of this debris will eventually intersect with the kind of Earth's orbit. Here's the orbit of this asteroid, which only completes its orbit in 1.4 years compared to Swift-Tuttle, which has a period of 133 years. I'll play that again. There it goes. We can see that here's the asteroid coming in, and right there on December 13th, 14th is where the Earth actually intersects the trail of this asteroid, and that's where we see the burst of meteors for its maximum at that time. Looking into the area of the sky where the meteors radiate from, they radiate from a position just above Geminid twins. And mark your calendars for this year. The observing is okay this year for the 13th through the morning of the 14th. The moon will be up, but it will set at 2:45 Pacific Standard Time. And so after that time, the sky will be dark enough to see these meteors. So I marked that down on your calendar. They produced 150 meters per hour in ideal conditions, so a lot higher than the Perseids.